Hey everyone, it's Mrs. H. We're going to lump 8.1 and 8.2 together, which is all of our variation. So we're going to start with direct variation. Hopefully you remember this from Algebra 1. You did do some of this in Algebra 1. How you did it may have been a little bit different. So we're going to start with our definitions here. Our definition for direct variation is basically a linear function where we have y equals mx. Sometimes you'll see it as y equals k times x, with k being our constant of variation. And this is basically a line, but a line that has no y-intercept, or a y-intercept of 0. So if we're thinking about this on a graph, I could graph this line, and it always is going to go through 0, 0, and then I have my different kind of ordered pairs on here. Well, our constant of variation here, m, again, sometimes you'll see that as k. This is like a constant rate of change. All right, and we did talk about lines at the beginning of the year. So just kind of keep that in mind as we go. When we're talking about this direct variation, we're going to say that y varies directly as x, and that's basically telling you which one is your independent variable and which one is your dependent variable. So let's take a look at a couple of examples here. We have the stretch in a loaded spring varies directly as the load it supports. Well, this is telling me that the stretch varies directly as the load, and so we're going to set up that y is our stretch and that x is our load. If I want to find the constant of variation, well, if I start with our equation here, y equals mx, I could plug in my values that I know. A load of 6, so that's going to be m times 6, stretches 8.4 centimeters. Now, you can keep in mind your units here as well. When I divide to get m by itself, I'm going to divide by 6 on both sides. I get that the constant of variation here, or in this case my slope, would be 1.4. What is that 1.4? That is 1.4 centimeters per kilogram. So it's kind of giving you that constant rate for how much this spring can handle. Now, for part B, we could answer this a couple of different ways. Because we just found what the slope was, what that m value was, I could plug in y equals 1.4x, and then I'm given the stretch, so that's my y value is 21, and I could solve for my x value this way. I could solve, and I'm pretty sure we get 15. What is the load measured in? It's measured in kilograms. Let me just double check that math on my calculator here. We do get 15. Good. Now, the other way that you could do these problems, though, because you know that the slope is the same at between any 2 points, you can actually set up a proportion instead. Notice how over here we divided. If I divide my equation, I'm always going to get y divided by x is equal to m. And so I could set up 2 ratios. The ratio that I know is 8.4 over 6. The one I'm trying to find is 21 over the load. And now I could cross multiply. If I cross multiply this, notice I still, if I did it out, get 1.4 equals 21 per load, cross multiply and divide, and I get divided by 1.4. I still get 15, and I'm still measuring in kilograms here. The other thing with your units is that they match up, right? It's It is centimeters per centimeters and kilograms on the bottom. So everything matches up nicely. I'm going to guess that you probably did it this way in Algebra 1. And so now we can use the proportions a lot more. So let's kind of formalize that here. When we're using proportions, if I have my ordered pair number 1 and I want to find what m is, well, I just divide both sides by x1. If now I have another ordered pair and I want to find what m is, I just divide both sides by x2. That constant is going to be the same, and so this can lead us to that we have these ratios that we can set up in a proportion for any direct variation. This can help us figure out some of our problems. I'm going to leave 2 and 3 for you. The only thing I'm going to add in about number 3 here is to make sure that the order of your ratio is correct. I know the ohms vary directly as its length. So this is going to be ohms over length when you're setting up your proportions. So go do those ones, check them. I will include the answer key when I post these notes. We are going to, though, take our direct variation and take it one step further. We know the basis of direct variation, and now we can have non-linear direct variation. So these are kind of the two ways that you can see it. The setup is all very, very similar. You just have to be careful with your wording. All right, so this one, let's see. The period of the pendulum, so that's how far it takes to go back and forth for one trip. Sometimes you'll talk about period with trigonometry graphs that you'll see next year, and you kind of do one loop, and then what happens is this shape happens again, and the period is that one kind of little repeat there. The period of the pendulum is directly proportional to the square root of the length. So I'm going to basically set this up the same way. The period, I'm going to use p. The square root of the length is that thing that goes on the bottom of my ratio. Now I can fill in what I know. Let's see. In one color, if a pendulum that's 49 long has a period of 2.1, so I'll fill in 2.1 for the period, root 49 on the bottom. For my second piece of information, what is the period? That's 1 meter long, so I'll call that p, and the square root of 1 goes on the bottom. This is now what I'm going to solve. Oh, but wait, we missed something. This is centimeters, and this is meters. So I don't want 1. I'm going to change that to be 100. You do want those units to still match up. I know the square root of 49. I know the square root of 100, and so I can cross multiply. I'm actually only going to do half of my cross multiplying. So I'm going to multiply up. I'm going to get, for this problem, 21 over 7 is equal to the period. Well, that means that the period is going to be 3. What was I measuring in for time? It's seconds. And so this will also be seconds. Last one for our direct variation, and that's the distance of an object that's falling from rest varies directly as the square of the time that it has fallen. So I'm going to write this in words first. Almost always I write these in words off on the side to keep track of what's what. The distance that this object falls varies directly, so I can set up a ratio as the square of the time. So that's going to be time squared. All right, now let's see. If the object fell 4 feet during the first half second, so the distance was 4 feet, the first half second is going to be 1/2 squared. How far did it fall during the next 2 seconds? Well, all I need is the distance during those next 2 seconds. But how long did it fall total? Because notice the time it's fallen total. So how long it has fallen is 2.5 total. This is the proportion that I want to solve. First thing I will do is I will square 1/2. That's going to be 1/4. 2.5, I'm going to rewrite as 5/2, and then I'm going to square it. And so this becomes 25/4. You do, in fact, know how to deal with a fraction divided by a fraction, but don't do it. It's a lot nicer to just cross multiply in this case. So I'm going to cross multiply. 4/1 times 25/4 is going to be equal to 1/4 times d/1. In this case, my 4's cancel, so I just have 25 is equal to d divided by 4. And the way I say it like that is because now to undo dividing, I can just multiply. What is the distance? The distance that it falls in the 2.5 seconds is 100 feet total after 2.5 seconds. What did they ask me though? They wanted how far it fell during the next 2 seconds. So I've got to take away that first little bit. If I take away the first 4, now it has fallen 96 feet in those 2 remaining seconds. So total after 2.5, it was 100. All right, I know that was fast, but hopefully that made sense. You have some book work to try. I'll post a note about this when I post the video. Let's move on and talk about inverse and joint variation. Again, hopefully you remember these from Algebra 1. Really nothing too new. First, our inverse variation here. So let me switch colors. Our inverse variation, this is probably the formula that you remember from Algebra 1. Were I to cross multiply, I can also think about it like this. We do have a couple restrictions. I think I forgot to mention those restrictions for direct variation, but you don't want to have zeros because that just kind of messes everything up. So x isn't 0, and in this case, k isn't 0. Our constant of proportion, or our constant of variation, is k. What does this graph look like? We actually have seen a graph similar to this before when we did our parent functions graphs, but it's been a while. This is kind of a funny curve like that. We'll talk more about these as we go. Let's do a problem. Again, pay attention to the vocab here. Y varies inversely as x, or y is inversely proportional to x, means the same thing. Number 1 here, if y is inversely proportional to x and y equals 2 when x equals 6, I want to find y when x equals 3. Well, back in Algebra 1, when I do these problems in Algebra 1, I often do these as 2-step problems. I do y equals k times x, but wait, what do I know? I know y is 2 when x is 6, so what's k? K is 1/3. Whoops, I said 1/3, I wrote 1/2. Then I switch and I say, okay, let's see. Now I have y equals 1/3 x, and I know that y is 3. So I have 3 equals 1/3 x. Shoot, I did something wrong here. What did I do wrong? 2 and 6. Oh, what am I doing? I am doing the direct variation. I'm sorry, everybody. Let me just fix that really quick over here. K divided by x, whoops. So it's k divided by 6, so I get that k is 12. Okay, that makes a lot more sense. Really easy to make those mistakes, so be careful. Over on this side now, I'm going to have 12 divided by x. So I get... Let's see, 3 is equal to 12 divided by x. I'm going to cross multiply and divide, and I get that x is equal to 4. We're going to see, though, that we don't necessarily have to do that. Like before, I am going to solve for, whoops, not the color. I'm going to solve for k, and I get that same thing. So every time k is equal to xy, let me do this in a new color here. So what you can do is you can just multiply x and y. I know 2 times 6. I also know 3 times x. Well, all I need to do here is divide by 3. 3 goes into 3 once, into 6 twice, and I get the same answer. I get x equals 4. This is kind of our Algebra 2 way. In purple is the way I do it in Algebra 1. All right, and last, we have joint variation. Joint is generally direct variation, and it's when you just have more. So often your joint variation, let's do green here, is going to be y equals k times x times z, or something like that. In this case, they're going to tell me a little bit more. Because it's direct variation, I can still set up that ratio. So when they tell me in number 2 here that z varies jointly as x and the square of y, that tells me that z is over x, and in this case doesn't mean times, it means multiply. The square of y is going to be y squared. Now I can set up my proportion. I know, let's see, 18 and 6 and 3, so there will be 3 squared. I'm finding z when I know 15 and 4, so that's being squared. I'm going to cross multiply. I'm actually only going to do half, so I'm going to cross multiply my 15 and my 4 and 4 up over here, and let's see what cancels. 3 goes into 3 once, into 15 5 times. Let's just do 6 goes into 6 once, and into 18 3 times. Oh, and then look, my 3 and 3 cancel. So I have 5 times 4 times 4. So what is z equal to? It's equal to 20 times 4, which is going to be 80. All right, so you can kind of do these bit by bit. Of course, you can go back. You can use your equation. You can find k and then solve from there. Or you can use those proportions that you know. I think everything else is pretty straightforward. So again, I'm going to leave the rest of these questions for you. Except let's do one. I think you can do this on your own. So try these 2 problems with joint and inverse variation. Set them up. You can absolutely use a calculator on a question like number 5. I will include the answer key when I post this, so double check, and then of course we can answer questions in class. All right, thanks everyone.